For this wrap-up, I've prepared some tables on the manipulators organized by the particular header. So in this example, we have the stream manipulators from the O stream, starting off with the inline and the flush. Inline, of course, is going to insert a new line and flush, whereas the flush is only going to flush the output stream. It's not going to insert the new line. Some of the stream manipulators from IOmanip, we have set W to change the width of the field, and then set precision to set the number of digits to use to represent floating point types. Then we have set fill, which is going to change the field fill character. We also have set iOS flags, which is going to set the specified iOS base flags, and it kind of behaves like the shout.setf function. We also have the reset iOS flags, which is going to clear the specified iOS underscore base flags, and that behaves like the unsetf member function of cout. Here are some examples on the setf and the reset iOS flags. Again, one is a member function on cout and the other one is that manipulator. But in both of those we pass in those constants, such as standard iOS show pause, for example. Just to reiterate on this, we have seen the slide before, but at the bottom there in those examples we can see that we have public member functions, such as the width member function on cout. We pass in the width that we want there for the field width. Then we also have public member constants, which are used as arguments for iOS base FMT flags. Here we are doing standard iOS base, show base, for example. Then you also have those global manipulator functions, such as standard set W. Again, those are global, so there's a difference again between the member functions, the global manipulator functions. And then we also have those constants, as we've seen in the previous slide. We can pass those constants into set flags. We can also pass them into reset flags. That is to reset those flags back to the defaults for the particular thing, so for floats, for example, or for integers. Next we have the manipulators from the iOS files. We've seen the bool alpha and the no bool alpha, which is going to set the boolean output format. So we get true or false instead of zeros and ones displayed. Then we have fixed and scientific, which is going to set floating point output format. Then we also have the left, right, and internal field justifications, and I've demonstrated the difference between those. Right is going to justify your output within that field width, and for the internal justification, it's going to sort of separate out your sign or your prefix if you have a different base. It's going to separate those out. Again, it all depends on the kind of output that you want. A couple more manipulators from the iOS file. We have no show point and show point, which is going to set whether decimal point is displayed or not. Another one that we've seen quite a bit here is the show pause and no show pause, which is going to set whether or not we want to show the plus sign for positive numbers. Uppercase and no uppercase is going to set the case for digits for hexadecimal. And then we also have the base number system, which we can change. So we can change from decimal to octal, for example, or to hexadecimal if you want to display in a different base number system. And then finally we can also show that base by using the show base manipulator or the no show base to turn that off again. For example, we can set whether a prefix should show up to indicate what base is displayed. Again, 0x for hexadecimal or 0 for octal. Okay, let's recap the default formatting for integers and also the formatting options that you have for integers. Also note that these settings will persist until they are changed or reset. So the default formatting for integers are decimal, so base 10, no show pause because the plus sign is not displayed for positive integers, and no show base because the prefix for octal and hexadecimal values are not displayed, and then also no uppercase because hexadecimal values are displayed in lowercase by default. For an exercise, think about what the default formatting for floating point types are. When I come back, I will summarize that for you. Alright, so the default formatting for floating point types, set precision is 6, so the default precision is 6. That is the number of digits that are displayed before and after the decimal. By default, we do not have fixed and we do not have scientific notation. So in the default floating point notation, precision specifies the total number of digits before and after the decimal point. And as I mentioned, the default for that is 6. Whereas in fixed and scientific notation, the precision specifies how many digits to display after the decimal point, even if the digits are zeros. We also have no show point because no decimal point is displayed if there is no fractional part, and we also have no trailing zeros. No uppercase because lowercase e is displayed for scientific notation by default, and then no show pause because the plus sign is not displayed. Finally, we have no show pause because the plus sign is not displayed for positive floats. For this quick example, I have a couple of doubles here. T1 is initialized to 1 to 3.321. T2 is initialized to 1 through to 9. And then I also have this T3 here. Alright, so in the first couple of printouts, I will print out the default display with precision 2. Okay, so I have the set precision here. I changed that from the default, which is 6, to 2. Then I go and display those 3 doubles. Next, I have fixed, so I change the formatting to fixed, and then I go and display those again. And then I change the formatting to scientific, and then I go and display those again. So if I build and run that, we get the default display with precision 2. So we get 2 significant digits, and then in the fixed point notation with precision 2, the significant digits will actually follow the decimal point. So you can see we have 1 to 3.32, and then for D2 we actually get the decimal point followed by 2 zeros. And then for scientific notation, that will also follow the decimal point. So we have the decimal point 2, 3 here. Also notice that I'm displaying the positive sign, and I'm displaying the E capitalized, whereas with the default display, the E is going to be lowercase. And that's because I have show pause right here and standard uppercase. Okay, so to recap, with the default display, the significant digits are before and after the decimal point, whereas with fixed and scientific, the significant digits that relates to the precision follow the decimal point, alright? I want to get back to this example to show a couple more things. I have a couple of doubles up here, and then I display those in the fixed point notation using setf. I pass in that fixed here to set that, and then next I do scientific notation, and then I want to revert back to the default display. If we build and run, we get this sort of output. We get the fixed point notation, scientific notation, and then we revert to the default display. I also mentioned why we use this flag function instead of something like setf. Because if I have setf here and I use scientific and show pause only, then that will not unset that fixed point that we have at the top. So of course we can go and unset that, or what we can do is we can use the second argument. I'll just do control so spacebar here. We have different overloads for this function, one that takes in 1 argument and one that takes in 2 arguments. So we have new flags basically, and then we have a mask. So let's look at the second argument here. I'll do setf scientific, and I'll actually just remove this here. Now what is the second argument going to be? The second overload is going to set the flags that are in both the first argument basically right here and the second argument, which is the mask, and it's going to clear the flags which are set in the second argument, which is the mask again, but not in the first argument. For the second argument we can specify a field, a base field, a float field, or a just field. This one right here, the scientific, relates to the float field. Okay, I talked about these different fields in the FMT flags documentation that is on c++.com. We have the field or flag value to the left, and then we have those equivalent to those member constants. So this is going to clear fixed because that is not in this first argument. Build and run. Notice that it clears fixed and it's going to set the scientific notation. Also, instead of using unsetf here to clear the scientific, for example, I want to do reset iOS flags, but before I can do that I need to include that IOmanip. For this we can now pass in that float field. If I build a run now, notice that that has cleared the scientific. So this sort of thing, with setf, we are going to clear the fixed, and then here we are going to clear whatever is currently set with the float field. We're going to clear the scientific, which we have set at the top here. Of course, you can always use this up here as well, and then maybe notice that the scientific notation is not going to actually display in fixed as we had it before, because we have that commented out. We have setf commented out, and then we have this reset iOS flags, which is going to reset what we have in the float field, which is going to be fixed. So I'll just comment that out. I just wanted to demonstrate this because you can see this sort of syntax And it can be a bit confusing, but I just wanted to demonstrate that so that you have a basic idea of what is going on. Of course, we don't need the show pause here, since we're not setting that anywhere. I will do some cleanup and remove that statement right there. And of course, we don't need to use reset iOS flags. What we can do instead is the statement right here, unsetF instead of reset flags. For the first printout, I want fixed notation, and for the second printout, currently we have scientific notation, but let me go and change that back here. We do the setF when we pass in scientific, so up here we do setF when we pass in fixed, and then we do scientific. If you remember, if I build and run this, we should get some weird printouts here. And if you pay attention, we get 0x here. So basically what we get with this is that floating point values are written using hexadecimal format. And that is basically the same as doing this. Okay, so that is basically the same as doing this, scientific and fixed. I'll just comment this one out here. Change this here from scientific to hexadecimal format. Again, build and run. You can see those printouts start with 0x, so we get that hexadecimal notation. Now there's a different way of doing this, so instead of doing this line right here, what I can do instead is I can use the xfloat manipulator, build and run, and notice that we get that hexadecimal notation again. So how do we set that back? Currently we are doing unsetF, and then we are passing in iOS float field, again to get this sort of result. Now what we can also do is, we can use default float. Essentially this is going to set the float field format flag to default float, or in other words the floating point values will be written in the default notation. Okay, so let's try that. If I build and run, notice that we get that default display for the floating point values. Again, without that, if I comment out that line, the final printouts will not be in the default format. Okay, so just wanted to wrap the section up by explaining what those weird printouts were that we got before. Those were floats, but they were in hexadecimal notation. And I also wanted to mention you have the default float option and the hex float here as well. You don't really have to remember all of this. This is in the documentation. I just wanted to demonstrate this to you in the case where you run into an issue or you see it in someone else's code and you don't know what those are for. And I also wanted to demonstrate the different fields, such as float field, for example, and how you can use those, as I did in the previous example. Since we are wrapping up the section where we discussed the manipulators, I want to discuss the field width again. So for this particular example, I have a helper function, which I named numberRuler, that is going to accept an integer. The formal parameter is called iterations because this is going to print out a numberRuler. You can see the string here is 1 to 0, 1 being the start and then 0 being at the end here. That is for tens. So by default, this helper is going to print out this string here 4 times, and it's going to end that off with a new line as well. Alright, so in the main function, you can see I use that helper every time here before I do a printout. So with the first printout here, the statement where I print out hello, a field width for that is not set. But in the next one, we do have a field width of 10, so we do set W and we pass in 10 for that. And I'm going to print out hello again. I will build and run, and we can see in the first printout we get hello. It is not in a field, and the second one is within a field that has a width of 10. As I discussed in this section, the field is going to be right justified by default. You can see the O of hello is going to be right underneath the 0. And in the next one, we can see hello is left justified. In this section, I simply do a left justification, but by default, we use whitespace for the fill characters, so we can change that. We've seen how to do that. We use set fill, right? You can add some character like that, for example, and then we go and set the width again to 10, for example. I set that to left again for this example, and then I print out hello, but then notice I do another printout, Bob. And this statement is to demonstrate that The field width such as here with set W is only going to be applied to the next data item that will be output. In this case, this hello string is not going to be applied for the entire statement. It's only going to be applied for this next data item, which is to be output. Alright, so if I build a run, remember that in this final output, hello is left justified. The field width is 10. We've changed the fill character, so that will now show up and will fill up the rest of the characters. Bob will be left justified, and we do not get the fill characters because a field width is not assigned to this Bob string, right? So I just wanted to recap that, and again, this sort of ruler makes it easier to sort of visualize what is going on if you want to do a write justification, such as let's say we do write again here. In that final output, notice that the full characters will now be to the left. And then of course you can also change the field width, or you can set up a variable that you pass in for that as well. Okay, so if you have trouble visualizing what is going on with the left and right justifications, for example, then you may want to set up some sort of an example like this. Of course, you can set up your function the way you want. This is just a quick example here. To wrap up, I want to discuss the different built-in or fundamental character types that we have. In the first column, we can see the type, and then we also have the bits. And then we actually have some prefixes, and then we also have a matching standard string type such as std string, and we have an example character definition because some of these, as I mentioned, have a prefix. So we are familiar with the char already, and then we also have something called a wchar_t, which is a wide char. The wide char wchar_t is an implementation defined wide character type. In the Microsoft compiler, it is a 16-bit type. We also have char16_t and char32_t. with 16 and 32 bits respectively, and then C++20 introduced the char8_t, which is 8 bits. Notice the prefixes for those, so for the wchar_t, the wide char, the prefix for that is an L. Notice in the example definition, we prefix the character with an L. The prefix for the char is either none, as we are familiar with already, or U8 prior to C++20, and then for the char8_t, that is U8 since C++20. The prefix for char16 is lowercase u, and the prefix for the char32_t is uppercase u. As I mentioned, we have the matching standard string types as well. We have the standard string for the char. In other words, we can store a sequence of chars in a standard string, and we can store a sequence of wchar_t in the standard w string. And we have u8 string and u16 string and u32 string for the char8, char16 and char32 respectively. So we have the signed char, but we actually also have the unsigned char, as I mentioned in previous lectures, and that is often used to represent a byte, which of course is not a built-in type in C++. As we've seen, variables of type char also get promoted to int, as if it is from a signed char. This slide here summarizes that we have narrow and wide strings, strings of type or sequences of type char, or char8_t since C++20. Those are referred to as narrow strings, and then wide strings are strings or sequences of characters of the following type, wchar, char16 or char32. Although when we are referring to wide strings, we are typically referring to wchar_t. A quick example on the wide string and the narrow string. This here is a string of characters of type char, and we can assign that here to this name right here is a pointer to a character constant. If you want to do it in this way, then we typically want to use a pointer to a character constant as opposed to just a pointer to a char. Otherwise, use the array. Alright, as we are familiar with the previous lesson. The same thing goes for the other types. Next we have the wide string. This is also a pointer, but in this case it's a pointer to a wchar_t constant. And notice the prefix L. If I remove that, we will get to this warning here, this error. A value of type pointer to const char cannot be used to initialize an entity of type pointer to wchar const. Alright, so I'll prefix that with the L. Also notice that prior to C++20, you can either prefix your string with nothing, or you can use U8 like that. Also, if you want to use the char8_t, then you need to go to your project properties and make sure that you have your C++ language standard set to C++20 at least. And then we can see we do cout, and then actually for the wide string wchar, we are using wcout. Build around that, and that prints out fine. So the goal of this section is not to discuss the different character types in too much detail and encoding and all of that stuff. I just wanted to introduce those different character types because I wanted to mention that we have different output and input objects. For example, we have WCOut as we can see here. So I will talk about that in a bit more detail in the next section. I've discussed the global stream objects before: standard cout, standard cin, standard CERR for the standard error stream, and then the clog as well. Now I actually have the wide stream objects as well for the wchar. That is going to be standard wcout and standard wcin, standard wcerr, and then standard wclog. Similarly, in this section I introduced the printf function. So for the char sequence we'll use the regular printf function. I have an example on the definition of that. The formal parameter is pointed to a char constant, but then we also have a wprintf, which has as a formal parameter a pointer to a wchar_t constant. Alright, so we're not going to pass a sequence of wchar_t, a wider character sequence, to printf. We are going to pass that to wprintf. And then just some examples on the character string and the wide character string declarations and initializations, and then the printf and wprintf invocations. Some more examples in Visual Studio. I'm using this namespace standard string literals for the s suffix. I will use that here in just a bit. Then we have these two character strings. One is a C string, and this one is the wide C string. I also have these declarations, a standard string and a standard W string. Notice for the wide character string and for the wide string object here, we use the L here when we do the initialization. Otherwise, again, we will get an error. Just undo that. Then I have another string object declaration, string 2, but in this case we are using the raw string literal. Of course, we can use this backslash character. And we have another wide string, but notice how I go and initialize that. I use LR, so I'm using the raw string literal syntax, but I'm prefixing that with the L. And then I go and print those out. Build a run here. Alright, so this is what we get. I've commented these two strings out. Here I have a wide string and I'm doing concatenation. But if I build, we cannot add those two pointers using the plus operator. So instead of casting like this, so instead of having to do this sort of cast as we would have to do with a string, so for example, in previous examples I also mentioned that we cannot do that with the standard string objects. We have to convert one of those to a standard string object and then do the addition, because the plus operator is overloaded and will work with that. But what we can also do is, instead of doing this sort of thing, we can use the s suffix, which is from this namespace right here, string_literals. That will now construct a string, a standard string object, and then we can do that addition. And in a similar way, for the wide string, instead of doing this sort of syntax, we can use this sort of syntax. We prefix with an L to get the wide string literal, and then we do the s suffix. Just change that here to string 4, and if I build, that will build fine. One more place where you can use the s suffix is right here, where we do the declaration, for example. Let's say we have auto here. Now, what do you think wide string 2 will be? Well, that is going to be a character string, basically a pointer to wchar_t constant. But later on in our code, we may want to call functions, so member functions on that string object. But of course, we don't have members on a wide character string. So we can change that. We can use the s suffix. And now that is going to be a standard wide string object, which of course will have member functions. And we can build and run that just fine. Alright, I just wanted to give you a simple example on this. We are not really concerned with the wide string types. We are primarily concerned with the standard string and then of course the regular character string. That is for this course, but you may come across the wide string and the other types of strings in other courses. So I've decided to demonstrate and to summarize some of these things for you.